When training a neural network model or even a univariate linear regression model using Keras TensorFlow, many times you will notice that your loss does not go down as your epoch increases. And one of the reasons why this happens is because your input data is not normalized. That is, your input data has values that range anywhere from 0 to 10,000 or even 100,000 and so on. So if your data has such large numbers or such a distribution where the numbers range from small to very big numbers, then something that you should definitely try is to normalize your data. And you also have to always remember to unnormalize the data or recover the predictions from the model after you have trained the model and made prediction from the model. Let's see how. Say I have a standard training code that looks like this. I load the data and then I open it in pandas. I check for any obvious errors in the data, and then I load the data using NumPy. I select the columns that I would like to load. I check the number of rows and the number of columns, and then I build a TensorFlow model, compile it, and then I fit the model. And then this is what I can do to make predictions from my model. Now say that during this process, as I do model.fit, I don't observe uh, expected improvement in loss, or as the loss doesn't go down as soon as I would expect. So then one option to explore is to see if we can normalize the data, and let's see how we can do that. So after we have loaded the data using pandas, we can do data.head to look at the first few rows of data. And here we check for any possible errors. So then the next thing we do is load the data using NumPy, and we check for the shape of data. So now after this, before we would like to feed the data to the model and do the training, what we would like to do is normalize our data set. So for this, what we would like to do is first visualize how the distribution of our variables look like. So I'm going to import matplotlib first. And then next, we would like to pick our, let's say, the first column variable. So I'm going to do plt.hist, which is basically histogram. And I would like to plot the histogram of my data set, all rows, and my first column. And let me also name this histogram. So looking at this histogram, we can say that the blood pressure values range from 0 to 120, and that most of the values are between, say, 50 and up to 100. Similarly, I can also choose to plot the histogram of age values, and for that, I simply choose the second column, and then I change the title as well. So these are the age, this is the distribution of age, and we can see that the age ranges from almost around 20 to up to 70, and most of the ages are between 20 and 40, 50 up to. Now, interestingly, for reasons that we will not talk about in this video, neural network models find it much easier to learn from data which range from 0 to 1, or at least around 0 to 1. So for that reason, we would like to change our variables values to numbers between 0 and 1. And one easy way to redistribute our variable values to between 0 and 1 is to simply divide by the maximum. So for the first variable, let's say our variable blood pressure, let's calculate the maximum first. So I'm going to do BP max equals data set, all rows, and column 0 dot max. And similarly, I can also calculate age and go age max equals data set 1 max. So this gives me the maximum values of BP and age. So I can do print BP underscore max and age underscore max and see what they look like. So the maximum BP is 122 and maximum age is 81. Now we can simply divide all our ages and blood pressures by the maximum values so that all numbers will now range between 0 and 1. So for this, all I have to simply do is set dataset 0 equals dataset 0 divided by BP underscore max. Similarly, I will do the same thing for age as well. Dataset 1 will be dataset 1 divided by age max. So now we have normalized the data in a way by simply dividing by the maximum. Now let's go back and redo the plot to see how they look like. So I'm going to simply copy this code and redraw the plots after our normalization is done. So let's plot the age values after they have been normalized. So we can see that in this plot, the distribution of ages range from 20 to 80, whereas here the y-axis is still the same, the distribution still looks the same, the histogram looks similar, it is exactly same. The only thing that has changed is the values in the x-axis. In other words, now all the ages have been converted to a number that is less than 1. So the maximum is now becomes 1, and all other values become similarly smaller. We can also similarly compare the plot for blood pressure as well. Now, after we have done this, we can run our regular TensorFlow Keras modeling pipeline to do the training. So here what I'm going to do is simply run the prediction by setting verbose equals 0 so that I don't see a lot of output in my screen. And then I do model.predictions equal model.predict. Here, what I want to supply is my data set 0 as my input. And now I have my predictions from the model. So if I do print predictions, and let me print the first 5 values, then these values are actually numbers less than 1. So obviously, they cannot be predicted as values. So how do I recover the actual is predictions from my model's output? So to do this, what I can simply do is, earlier we had divided by the maximum. Now we can simply multiply by the is maximum. So I can simply do actual predictions equals predictions times is max. And this gives me the actual is predictions. And then now I can go and reprint the is values, but this time I'm going to print the actual predictions. So actual is predictions, first 5 values. And these are the actual predictions that the model is making. So this is a very trivial or a very simple way of doing normalization and actually recovering the predictions or denormalizing your data after making predictions. After we have normalized the data, we usually don't worry about the normalized data, but to actually deliver the prediction, we always have to recover the prediction. Something that's very important to keep in mind is that we have to calculate this age max or maximum value of age before we do the training. And this value of age max needs to be kept or calculated and stored somewhere before we do the training, so that after the training we can use this stored normalization parameter to recover our predictions. Now, dividing by maximum value is not the only way to normalize data. We can bulk normalize our data, that is, bulk normalize all our input features at once and recover them also at once. What's very important about normalization is to understand that we should only pick one normalization technique, not all. So let us discuss various ways to normalize data. Say, for example, we have the PIMA Indian diabetes data set as our input. We load all the data set, print the shape, right? And then what we do is we simply split our input and output. So all the variables except the last one, we put into X, and the last variable, we keep it into Y. Now, the first type of normalization is the simplest one, that is rescaling that we just saw. So in this normalization, we simply do y equals y divided by y dot max. Now, here I'm only explaining the idea of rescaling, but if you actually do the rescaling, you now already know that this value y dot max needs to be stored in a variable somewhere such that we can restore them. We can do the same thing for x input features x as well. Now, standardization is a second technique or second way of normalizing the data. For this, we simply calculate the mean, and then we subtract the mean from our input data, and then we divide by the standard deviation. So this is next way of normalizing the data. You can do your homework to see if you have done this on your output variable, how can you recover it? We always have to store the mean and standard deviation for our values so that we can later use them to de-normalize our data. The next commonly used technique is min-max normalization. For this, what we simply do is calculate the min, max, and then we use this equation to transform our data from the given scale to a new scale which has minimum and maximum. So we simply do x minus min divided by max minus min. The last normalization technique is mean normalization. Here what we simply do is, instead of subtracting the minimum value, we subtract the mean and the average value. Now, the min-max normalization is one of the widely used normalization technique, even in methods like big data, because it doesn't take a very long time to calculate the minimum value and the maximum value. Whereas calculating average or even calculating standard deviation can take a lot of time depending on the data. So out of all of these techniques, one of the most widely used techniques is the min-max normalization. For smaller data sets, even standardization can be used.